We've seen the idea of an attention layer and a self-attention layer, and also multi-head self-attention. We're now able to put that into an architecture called the transformer, which is extremely powerful for a wide range of tasks. So let's see first how multi-head self-attention is combined with some other parts to create a transformer layer. So a transformer layer takes as input a d-dimensional or a set of d-dimensional vectors, so n input tokens. So we can represent that as a d by n matrix. And the final output is going to be the same size as the input. So what happens inside this transformer layer? So the key bit and most of the work is done by this multi-head self-attention. So remember, this is just a group of self-attention layers that are applied independently in parallel, and then their outputs concatenated at the end. Now, one ingredient in the transformer layer is this residual connection that provides the opportunity to skip past the multi-head self-attention. So this is the same argument as was made in the ResNet, that it's easier to learn the residual of the change in the representation you want rather than the new representation itself. And in practice, this helps stabilize training a lot by having, during backpropagation, the option for the gradient to flow directly round this skip connection. The second main ingredient here is that after the multi-head self-attention, the representations of each input token are independently passed through a neural network, so an MLP. So this is the same neural network repeated n times for the n input tokens. And another way you could think about this is one-by-one convolutions. So you've effectively got n sets of vectors with d channels, and you can think of each of these as being a one-by-one convolution layer that is independently applying these filters to each of the n inputs, so there's no sharing of information between them. And then again, we have a residual connection around these parallel neural networks. And the only other ingredient that I haven't mentioned yet are these layer norm layers. So this is something similar to batch norm, but we don't want, in batch norm we do normalization across the batch, and that would be across the tokens, and we don't actually want to introduce additional information between the tokens. That's already taken care of by the self-attention. So layer norm instead computes statistics across the tokens, but has a similar effect to batch norm, so it helps stabilize training. And just a reminder that multi-head self-attention is permutation invariant, so we can shuffle the n input tokens here, change the order of them. The parallel neural networks are applied independently as well, and layer norm is applied only to each token. So what that means is this whole thing, this whole transformer layer, is permutation equivariant. So shuffle the inputs and the outputs are just similarly shuffled, but they're unchanged. So now let's see how that transformer layer can be stacked into something quite useful. And the first thing we're going to see is a transformer encoder that can be applied to natural language. So the idea here is to pre-train an encoder that learns a good model of language understanding. So the input to the transformer is a set of word embeddings, and these would be augmented by positional encoding information, so that we know, or the transformer knows, that this token here, the start of the sequence, comes first, then this next token, the, comes second. Now, What we're doing during training is that we're randomly masking some of the words. So the sentence ends up reading as the something pulled into something station. The mask itself is a learned mask token, and the job of this encoder is to try to predict what those missing words are. And that's done with a series of transformer layers. So here we've got K transformer layers, and each of them contains the ingredients we saw before. So multi-head self-attention, and then these parallel neural networks. So the way to think about this is that after you pass through the multi-head self-attention, the representation for each token has benefited from some of the other information in the other tokens, because it's been able to attend to each of them and share information. So the output tokens after one of these transformer layers are no longer just to do with the word, they're to do with the word in context. So the word based on the other information in the sentence and how that might modify the word. And then you can think of these parallel neural networks. They give the transformer layer a chance to, having sort of received information in each token from the other part of the sentence, the MLP can now kind of reason just for this token. So it can say, okay, I learned some other information. So maybe I'm thinking about the word the. I've seen other words like pulled into station. So the, I'm starting to understand, might relate to something that pulls into a station. So that information is shared in the multi-head self-attention, but it's in the MLP where I can sort of digest that information and do something with it. So after applying K of these transformer layers one after the other, I'm now ready to make my prediction and to compute my loss. So for the mask tokens, I use a linear layer to project from my token representation to probabilities over my entire vocabulary. So here is like, if I'm using word embeddings, it's my entire dictionary of every word. And I end up computing a probability for every mask token. And now I can compute a cross-entropy loss and try and encourage it to predict what was actually masked from this sentence. So if I pre-train a huge model like this, it turns out to be very useful for other tasks, and I only need a small amount of fine-tuning to do that. So for example, I might decide to train for text classification. So now I want to be able to input sentences like the soup tasted like socks, and I want my transformer model to give me the probability that this comes from a review that was being positive about the restaurant. So the way I'm going to do that is take my pre-trained transformer, and that will output at the end representations corresponding to each of the tokens. But by this point, the token should have ingested all of the information from the other tokens and be very rich in their representation. And I'm going to choose to take the one that corresponds to this start of the sequence token, CLS, and that's the one that I'm going to extract the representation of the whole sentence from. So what I do is I fine-tune a small MLP that takes this CLS token and applies sigmoid to it. So I'm just trying, here I've just got a sort of, it's a single scalar score, and I'm going to use sigmoid to map it on a value between 0 and 1, and I'll treat that as the probability that this is a positive review. And I could supervise that with some labeled reviews that are either positive or negative. So in that case, I was trying to classify the whole text. But another application that I could fine-tune it for would be classifying the words within the sentence. So here I've got a complicated sentence. Zara works at Chanel in Victoria. So this, to understand the proper nouns in this sentence, so the fact that Zara is probably a person, Chanel is probably a business, an organization, and Victoria is probably a place, I really need the power of self-attention and the transformer to do that. So again, I take my pre-trained transformer model, and now on the end, I'm going to apply a linear layer to each of the representations for the tokens corresponding to the actual words, and then softmax so that I'll get probability across, in this case, the classes I'm interested in. So person, place, organization, or not referring to any entity in particular. And I can supervise that with a small data set and then only fine tune this linear layer at the end. And that will give me a way to do word classification with a relatively small data set. So now let's see the second way that a transformer can be used in language modeling, and that's in a transformer decoder. So this is similar to the autoregressive language modeling that we saw with a recurrent neural network previously. And the idea is to try to model the probability of observing n tokens as an autoregressive sequence. So I'd like to be able to say the probability of observing this whole sentence, "It takes great courage to let yourself appear weak," can be expressed as the product of the probability of seeing it as the first word multiplied by the probability of seeing takes, given that I saw it as the first word, multiplied by the probability of seeing great, given that I saw it takes as the first two words, and so on up until the last word. Now, we've already seen with the recurrent neural network that it's easy to compute these probabilities in an autoregressive manner. So that means making a prediction given the first set of words, predicting the next one, using the label to compute a loss for that, and then feeding that back in as the next word in the sequence. So that's exactly what we do. So I feed into my transformer this partial sentence, starting from the start token, followed by a sequence of tokens, and that goes into my transformer. And I'll come back to one detail of this transformer in a moment. And then at the end, I'm going to apply a linear transformation to the representations coming out for each of the tokens. And that will transform to the number of words in my vocabulary again. So this is now, after softmax, going to give me a probability over all of the words in my vocabulary. But what I want to happen is that when I've seen only the first token, which is just the start token, what I want to predict is the first word in my sequence, which is it. So I could compute a cross-entropy loss there. So you can see that this is really it's the input shifted back by one position, so that the first token has to get transformed effectively into the second token of the input sequence. And then what was originally it in my word embedding at the input, after passing through my transformer and turning into a probability distribution, I want it to choose the word takes. Now, one important detail is that the self-attention that's going on inside this transformer and all the way through this sequence of transformer layers, I can't, when I'm trying to look at this first token and turn it into the first word, I'm not allowed to look at information later in the sequence. So each position in the sentence is only allowed to attend to its own embedding and those of tokens earlier in the sequence. So I can achieve that using masked attention. I basically just cut off the connection, so we can see that the output for the first token is only allowed to attend to the first token. The second token can attend to the first and second, and so on. Only the last one can attend to everything. Now, what's amazing about these models when they're trained on very large input is they seem to become very good at few-shot learning. So I don't even need to do any fine tuning. I can just give it a large prompt. So just the context of the input. So imagine if I feed all of this text up until this point where the text changes color. And in this text, I'm providing, well, I'm writing as part of my input, poor English input, and then something that's not phrased very well, and then good English output, and then a sort of transformation of that sentence. So things like correcting eated to ate. So if I input all of that and then I use autoregressive prediction to make it keep just predicting the next token, the next token, the next token, it actually manages to continue this pattern. So here it corrects work with you in another project to work with you on another project. And it was never trained for that task. We haven't even fine-tuned it for this task. But there's enough context in seeing examples of good and bad English for it to be able to complete the sequence and provide me with a sort of translation to good English. Okay, the last setup that we'll see for transformers is basically just to combine these two things, and that lets you to tackle sequence-to-sequence tasks. And this makes a slight change to the transformer architecture. So what we do now is, if we're trying to tackle, for example, the task of translation, the encoder receives the whole of the input text, so the text in kind of language 1, and that's allowed to use full self-attention to fully understand its representation of this input sentence. So you can think of the output coming from this encoder. It's like a heavily processed version of the input tokens. So think of this as a sort of high-level contextualized representation where each element in this output set of vectors is now, it relates to the original input tokens, but they've absorbed a lot of information from the other input tokens and how they relate to each other. And at this point, this has got nothing to do with the eventual output we want, which is a translation. So instead, it's just sending this sort of representation of the input sentence. Then in the decoder, we're doing a bit like we did before with the autoregressive generation. So we're feeding in the sequence of tokens up to a certain point in the sequence. And what it's going to output is the input shifted by 1. So again, at the end, we're going to have this linear and softmax layer to map to a probability distribution over the tokens. This time it's over the French words, if we're translating English to French. And they're shifted by 1 again. So the start token has to get transformed into the first word of the French, and so on until we predict a token past the end of the input. Now, again, we're using here masked self-attention, so we're not allowed at training time to look ahead in the sequence. We can only look at the tokens up to the current one in order to predict the next one. And this is useful at training time because it allows us to do the whole sequence in one go. We don't have to actually predict just one token and then go back and do it again. We can make the whole prediction, and the attention is kind of fair. It's doing what would actually be available at generation time. But then we have this extra important part, which is attention, but it's cross attention. So now we've got coming from the encoder, this representation, which is sort of encoding all of the original sentence. So at this point, I'm now sort of translating the representation, the tokens, to also incorporate some information about what I got from the original sentence. And this is where the translation is happening. So in this decoder, I repeat this block multiple times, and then I try and predict the output words. Now, at generation time, so not training time, then I really do have to do this one token at a time, because I have to pass in my token, pass in the encoder output, get my probabilities, and then choose the most likely word or sample from the distribution. Then I can take that new token and put it back into the input and continue to generate the next token. So that is extremely slow. It's expensive to do this sort of translation. So we saw in the second example there a transformer decoder, and if you've heard of GPT, which stands for Generative Pre-trained Transformers, that's exactly what a GPT is. It's just a very, very large transformer decoder, and they're pre-trained on huge data sets of English text. So let's look at sort of the scale of these models. So GPT-2 had 12 levels with 12 headed transformer decoders, so that each transformer layer had 12 heads in the multi-head attention. Total number of parameters 1.5 billion, and it was trained on the web text dataset, which is 40 gigabytes of text. GPT-3, a more recent model, same architecture but scaled up massively to 175 billion parameters and trained on a huge data set, so 570 gigabytes, which amounts to 499 billion tokens, and that's augmented by a few other data sets as well. So, okay, we've got this huge pre-trained transformer decoder, and we know that that can be used for autoregressive language generation. If we want to turn this into something like ChatGPT, like a chatbot, then we have to fine-tune it so that it will generate text that's in the style of a sort of two-way conversation. And this is achieved by fine-tuning these GPT models to achieve this. So there's usually two parts to this. One is supervised learning, where human trainers just provide conversations, so they provide both the human and the chatbot side of the conversation, and this gives direct supervision for the sorts of conversations we'd like it to be able to produce. But we also use reinforcement learning from human feedback. So the idea is humans rank responses that the model has previously given, so kind of how good they are, and then from that you can train a reward model that tries to copy those human ranks, so it tries to learn to predict how good the responses are in the way that a human would. And then we can use that trained reward model to try and fine-tune the model, so to produce responses that are rewarded more highly. And we can iterate this process a few times. So the last thing to point out is just that these sort of transformers have been applied to very different sorts of data. So one famous example is the vision transformer. So the idea here is you tokenize your image data. So we break it up into patches. They chose 16 by 16 pixels. So that basically just becomes, for 3 color channels as well, a 768D vector. So once you've done that, you can just pretend it's a word embedding. It's no different. It's just token representation. So these image patch tokens are fed through a linear projection, and then that is input into a transformer encoder, exactly like we saw for language modeling. As with language modeling, we use positional encoding so that it knows where the patch is coming from in the image, so we're just concatenating on a positional encoding of the patch number. And we also have this sort of start sequence, or CLS, class embedding token, which is the start of the sequence. And the contents of this is usually learnable of this CLS token. So this sequence of patch tokens is fed into the transformer encoder, And then usually what we do is we take the transformed representation of the CLS token at the output, feed that into some sort of MLP, and then do classification so it predicts probabilities of the classes. So this is just a very different way of doing image classification, but using this transformer architecture.